Okay, so let me start by let me start by recalling a little bit of what we talked about. Let me see, is this working okay? Let me recall some of the things we talked about last hour. So if we're given V, a smooth, let's say, projective variety of dimension n over the complex numbers, remember last hour I talked about various measures of irrationality. So we had the degree of irrationality of V. So this was the minimum degree of a covering, of a rational covering from V to Pn. Then we had the covering ganality. I'm trying to figure out how to, maybe I'll do it like this. We had the covering ganality of V. So this was the minimum ganality of a covering family of curves. And then we also had the covering, well, okay, I'm trying to figure out how best to organize I might switch boards here. And then we had the covering genus, which I'll write as covering genus of V, which was the minimum ganality, a minimum genus of a covering family. So a family of a covering family of curves. So that's a minimum geometric genus of a family of curves that covers a general point of V. So the idea was, as I discussed, the idea was that these give a way of measuring how irrational V is, or how much V differs birationally from projective space. And so, as I said in the end of the last talk, here I want to look at a different question. So I want to consider, let's say, smooth projective varieties of the same dimension n. So two different smooth projective varieties of dimension n, same dimension n over C. And I want to ask, vaguely speaking, how different are x and y birationally? So how much do x and y differ birationally? So how much do x and y differ birationally? Okay, so that's the vague question we want to consider. Okay, and so how are we going to think about this? So we're going to think about this by studying the birational complexity of correspondences between x and y. So they're going to be sort of just as in the case of measures of irrationality. Remember, there were sort of two kinds of invariants. We had degrees of mapping, and then we had these invariants coming from the geometry of covering families of curves. And so in the same way here, there are going to be two kinds of invariants, some measuring degrees of maps and some coming from covering families of curves. So let me start by talking about what we call the correspondence degree. So this is the thing that's the closest correspondence. So this is the thing that's closest to the degree of irrationality. So, okay, so let me underline this, and then I'll, so let me first of all explain what the setup is going to be. So this will be the setup throughout the talk. So we'll consider correspondences between x and y. So x and y, remember, are smooth projective varieties of the same dimension. And so we're going to consider correspondences. So those would be varieties Z that map to X and map to Y. So I'll use this A and B. And I want to assume this about them. So Z is supposed to be a smooth projective variety of dimension n. So the same dimension as these things, smooth projective variety of dimension n. These two maps, A and B, are supposed to be generically finite and therefore surjective. And then it's a kind of a technical assumption that isn't really going to come up too much, but I want to assume that Z maps birationally to its image in X cross Y. So Z should be birational to its image in X cross Y. And that has the effect of saying that the fiber the fiber of Z over a point in Y is a general point in Y. B inverse of a general point in Y is a subset of X, and vice versa. So this way, the fibers of the one map lie in the other variety. Okay, so we want to, the first invariant, which is the kind of the pair invariant, the pair analog of the degree of irrationality, is what we call the correspondence degree. So I'm going to define the correspondence degree between X and Y. So what I'm going to do is I'm going to take the minimum over all these correspondences Z, and I'm going to be look at the product of, so the minimum over all Z of the product of this degree and that degree. So it's the minimum over all Z of the degree of the map Z over X times the degree of the map Z over Y. Okay, so I look at all correspondences Z. I look at the degree of the map from Z to X, the map from Z to Y. I take the product of their degrees, and that's the correspondence degree. And so this is the natural analog of the degree of irrationality of a variety. Okay, so what can we observe about this correspondence degree? Well, first of all, it depends only on the birational class of X and Y, only on the birational classes of X and Y. And that's because if you replace X and Y by different birational models, if you replace X and Y by different birational models, then you can find a different model of Z that sits in this analogous diagram. So this depends only on the birational classes of X and Y. And evidently, the correspondence degree of X and Y is 1, if and only if X and Y is 1, if and only if X is birationally isomorphic to Y. Because birationally isomorphic to Y. Because to say that the correspondence degree is 1 means this degree is 1, that degree is 1. So Z gives a birational isomorphism between X and Y. Okay, and it's an amusing exercise to check that, in fact, this correspondence degree satisfies a kind of multiplicative triangle correspondence. And so it's an amusing remark that, in fact, the logarithm of the correspondence degree defines a metric on the set of birational equivalence classes of varieties of fixed dimensions. So defines an actual metric on the set of birational equivalence classes of varieties of a fixed dimension. So it actually defines a metric. Okay, so now we have this, we've defined this correspondence degree, but what can we say about it? So first of all, it's not unrelated to the measures of irrationality of X and Y. So our first proposition is that this satisfies an inequality as follows. So one has that the correspondence degree between two varieties is at most the product of their degrees of irrationality. So the degree of irrationality of X times the degree of irrationality of Y. So it's not arbitrary. If X and Y have relatively small degrees of irrationality, then their correspondence degree between them is also going to be fairly small. And why is this? So let's see why this is. So supposing you have, let me imagine that these are real morphisms. Doesn't matter. Supposing I take a morphism from X to Pn and another morphism from Y to Pn that compute the degree of irrationality. So they might not start off by being morphisms, but I can resolve the indeterminacies. Then, okay, so let me draw a little picture. So here I have X to Pn and Y to Pn. Well, what can I do? I can take their fiber product. So what I can do is I take Z to be an irreducible component, of their fiber product. So I form the fiber product of these two things. That might be reducible, but then I take an irreducible component. And so if I do that, then then this degree is less than or equal to that degree, this degree is less than or equal to that degree. So the product of the degrees over x and y is less than or equal to the product of the degrees of x and y over Pn. Okay, but now, so here's the intuition for this invariant. So I can, if I have two varieties, I can always get these kind of dumb correspondences by taking I map x to Pn, I map y to Pn, and then I can always take z to be the fiber product. And so there are always some dumb correspondences between x and y. And our intuition is that let me call this inequality star. Our intuition is that if this inequality is actually an equality, so if this inequality is equality, that means somehow that x and y are, so to speak, birationally independent. So the intuition is that equality in star. So if you have only if the minimal things are these dumb fiber products, this means this points in the direction. This means, roughly speaking, that x and y are birationally independent. So there are no interesting correspondences, small degree correspondences between them. And this is especially true. It's especially true if the minimum correspondences are fiber products. So especially if minimal correspondences are fiber products. So the intuition then is that if this correspondence degree is computed by this construction, and that's kind of the smallest correspondences you can get between x and y, that somehow is pointing in the direction of x and y being birationally independent. So let's do an example where you can see that this happens, namely, let's take the case of curves. So let's, as an example, say that x and y are very general curves of genera as gx and gy at least one. So let's say that x and y are very general curves of genus, of genera gx and gy at least one. Then I want to claim that we're in this situation of birational independence. So then in fact, the correspondence degree is the product of the gonalities. So it's it's essentially the genus of x divided by 2 times the genus of y divided by 2. And the minimal correspondences are this birational, and the minimal z are, they're birational anyway, 2 fiber products of the gonality maps. So for general curves, you're in this situation where the smallest correspondences arise like this. So you take the gonality map from x to P1, the gonality map from y to P1, and you take z to be essentially the normalization of the fiber product. And so why is this? So this is simple. So let's see why this is. So the point is, and this is how the game always starts. The idea is that x, if you take 2 general curves of genus at least one, they're, so to speak, Hodge theoretically independent. So the Picard group of x cross y, if they're general curves, is pic of x, is the Picard, for some reason this is trying. The Picard group of x cross y is the Picard group of x cross the Picard group of y. So there are no interesting line bundles on x cross y, just exterior products. So what does this mean? So if we look at the z, or rather I should say the image of z, but I'm just going to call it z. So z is the image of z in x cross y is some curve in this surface x cross y. The only line bundles in x cross y are things of the form line bundle in A pulled up, a line bundle in x pulled up, tensor line bundle in y pulled up. So z is given by a section it's the divisor of the zeros of a section of A exterior product B. So the pull up of a line bundle A from X and a pull line bundle B and Y. And then you see right away that this is only possible. A and B have to move in at least a pencil. I mean, they can't have just one section. Okay, so this says that the degree of x and the degree of z over x and degree of z over y is at least that's equal to the degree of A times the degree of B. So it's at least the product of the gonalities. And if z is minimal, then the only way this can happen is you have to have equality here. So if z is minimal, then you could get smaller degree things. If they weren't pencils to begin with, you could get smaller degree, you could impose base points. So then R of A and R of B has to equal 1. And then basically Z is the pullback of a divisor of type 1, 1 on P1. So Z is, and Z is the normalization of a fiber product. Okay, so this is kind of a simple example of how this, so for two very general curves, this correspondence degree, is as big as it could be, and you only get these kind of boring correspondences. Okay, so what I want to talk about now is, let's see what we can say now. Again, we want to kind of generalize the kind of thing we've said in the previous talk. So let's start by talking about hypersurfaces. So hypersurfaces. Okay. So we'd like to, just as in the case of covering gonality, we'd like to sort of say that if you take two very general hypersurfaces, they're, so to speak, is birationally maximum, they're as independent as possible birationally. So here's the theorem. Okay, so let's consider two very general hypersurfaces. So consider XD and YE in Pn plus 1. So these will be very general hypersurfaces of degrees D and E. Very general hypersurfaces of degrees D, E, and again, we want at least 2n plus 2, let's say. Okay. And then the theorem is that the correspondence degree in this case is again the product of the degrees of the irrationality. So it's as big. So then the correspondence degree between X and Y is the product of the degrees of irrationality. And remember, that's D minus 1 times E minus 1. And again, minimal correspondences are given by fiber products of projections from a point. And so, and minimal correspondences, again, are birationally equivalent to projections, to the fiber product of projections from points. Birationally equivalent to the fiber product of projections from points. Okay, so again, you get this kind of, they're in this sense, they're kind of birationally independent. So the proof, I'm going to say a little bit about it, but the idea is that it follows along the lines of, which I didn't talk about last hour. It follows along the lines of attack of the two papers of the measures of this paper by Bastianelli, Cortini, Dupoi, and this one with this group of people here for hypersurfaces. But I'm not going to really say too much, but I want to explain, so for measures of irrationality for hypersurfaces, but I want to explain the idea of what comes in, and I'll explain this by proving a weaker inequality. And so the idea is, and this is the idea that really goes back in a different context to Pirola, Parola and Bastianelli, Cortini, and Depoy. So we'll prove a weaker inequality. So I'll prove a lower bound on the correspondence degree that's not as strong as this, but it will explain sort of the beginning of the proof. Okay, and so the idea is that the first step, just in the case of curves, we want to say that if we have two very general hypersurfaces, they're in some sense Hodge theoretically independent. So the first remark is, and this is kind of a well-known fact, that if we take very general X and Y, there are no interesting maps between the Hodge theoretic maps between their cohomology. So the homomorphisms of Hodge structures between the, well, let's say the primitive cohomology of X and the cohomology of Y, there are no interesting maps, and vice versa. Okay, so for very general hypersurfaces, and again, this is something that goes back to Prolip. I mean, for example, Youngnam Lee has used the similar ideas to study. I mean, he has some very interesting work about if you have a general hypersurface, what can it map to? And again, the starting point of all of these things is that if you take a very general hypersurface, or two very general hypersurfaces, there's no interesting maps of Hodge structure. Okay, so how does one sort of say anything, use this to say anything geometrically? So, okay, so let's consider then a correspondence. So let's consider the correspondence between X and Y. So we have Z mapping to X, mapping to Y. And so this is A and this is B. And the situation is, of course, symmetric, but I'm going to break the symmetry just for notational purposes. I'm going to think of Z as giving a correspondence from X to Y. And so if I have a correspondence like this, I get an induced map both ways, but this gives, this Z gives me a map from the cohomology of X to the cohomology of Y. So it gives a map from Hn of X to Hn of Y. Right, I take a class here, I pull it up and I push it down. And that's a map of Hodge structures. So I also get a map on form. So I get also an N0 piece that takes the N0, the holomorphic forms on X to the holomorphic forms on Y. And what is this map? If I take an eta here, what I do, so eta is a form on X, I pull it back under A, so I take A upper star of eta, that's a form on X, and then I trace it down to Y by B. So let me just say that it's going to be important to say this kind of more concretely. So what this means is if I start with a form eta on X, so I take Z lower star N0 eta, this is a form, as eta is a form on X, this is a form on Y. And so how is this form defined at a general point of Y? So for a general point of Y, okay, so I start, so Y is here, eta is here. So what I'm going to do is I'm going to take, I take the sum over all points in the fiber of Y. So I look at all X in the fiber of Y. So Y has, I take Y down here, it has a certain number of preimages. But now remember, I can think of the fibers Y as a subset of X. And on the other hand, Z lets me identify the tangent space at X of all those points to the tangent space at Y. So I just take the sum of eta, so eta is a form on X, and I take the sum of eta over all the points in the fiber. Okay. And so this is what, so I get this is this very geometric thing. If I have a form on X, I can kind of trace it down to get a form on Y. Okay, but now what's the point? But now the point is that by step one, this has to be, I mean, this Z, this lower star N0 is a piece of this map on, this is a piece of a map on Hodge structures, but there are no maps on Hodge structures. So this map, Z star N0, has to be the zero map. So what that means is that this is what people call a null trace, has to be what people call a null trace correspondence. For any form on X, when I do this procedure, I have the form on Y I get has to vanish. So this has to be 0. So what this means concretely, and this is the idea, is that if I can find, if this form eta vanishes on all but one of the points of B inverse of Y, it must vanish on the remaining one as well. So if eta vanishes at all but one of the points of the preimages of Y, it must vanish at the remaining one as well. So this is what people call the Cayley backup property at remaining one as well. And why is this? Well, again, let's look at what this says. So I take this form, by what we've just said, this form has to be 0. So this has to be the 0 form. So what that means is if I take a point in Y here, and I look at its preimage, and if this eta vanishes at all but one of the points of the preimage, and if it didn't vanish at the last one, then it wouldn't trace to 0. So if I have a form that vanishes at all but one of the points and not at the last one, it can't trace to 0. But on the other hand, this form has to be 0. So to say that this map is 0 on forms means that if I have a form vanishing at all but one of the points of a fiber, it must vanish at another. But now you see, this is where the positivity of the N0 forms comes into the picture. But remember that the canonical bundle of X, KX, is linearly equivalent to D minus N minus 2 times a hyperplane class on X. And this line bundle, just it's elementary, this separates, since this separates any D minus N minus 1, separates any D minus N minus 1 points on X. So what that means is this condition, if the degree of this map were D minus N minus 1 or less, this couldn't happen. If this map were degree D minus 1 or less, I would be able to find forms that vanish at all but one of the preimages, but not the other one. So this means that, so this forces the degree of B to be at most D minus N. And the situation is symmetric, and similarly, the degree of A is at least E minus N. So this is, as I say, this is the idea that goes back to Parola, maybe it goes back farther, and Bastianelli and Cortini and Dupuy. So this proves a sort of a weak statement. For the stronger statement, and this is the sort of second half of the argument, this is, you sort of use the fact that it gets into some projective geometry. Use the vanishing of these maps Z lower star and Z upper star to show that the fibers actually span lines in their relevant. See, this is in their relevant projective spaces to show that Z, the fiber of Z over Y, that's a subset of X, and the fiber of point X, which is a subset of Y, actually span lines in Pn plus 1, and then you use some sort of fun geometry of, and then you argue geometrically. And again, in the end of the day, it reduces to, so there's a little bit of Hodge, some so geometrically. There's some, again, a little bit of cohomological argument. And at the end of the day, you reduce to some computations of Laurentin and Voisin, sort of to the effect that there's that things kind of behave, there's some kind of hyperbolicity for very general hypersurfaces. Okay, so that's the story there. Now there's a variant of this that seems interesting. There was a raised by Jordan Ellenberg. So what you can do is, instead of looking at correspondences between two very general hypersurfaces, you can look at what you might call autocorrespondences. So Ellenberg asks, what about autocorrespondence? So what about correspondences between X and itself? So what about what you might call autocorrespondences. So in other words, let's look at the correspondence degree. I'm going to leave a little room there, of X with itself. Now, obviously, this is kind of silly because X is you can just take the identity. So what we should do is we should put a little NT there. So this would involve, so here I want to talk about, these are kind of correspondences that you look at correspondences where you exclude the diagonal. So look at correspondences other than you sort of correspondences and you exclude the diagonal. So you kind of throw away. So of course, any variety, there's always the identity map next to itself. So that would have correspondence, that would give you a correspondence degree of 1. So the question is, are there any interesting correspondences from X to itself? What can you say about correspondences between X and itself when you kind of throw away the identity? And again, so let me call it a conjecture / theorem. I think we know how to prove this. I think we more or less know how to prove this, but we haven't written it out. So I'll call it a conjecture theorem. But so the claim is that in the situation of the theorem before, so with X as above, so XD in Pn plus 1, very general of degree, at least let's say 2n plus 2, then the claim is that the conjecture of the theorem is that this autocorrespondence degree, there must be a better name for it anyway, between X and itself is d minus 2 squared. So where does this d minus 2 squared come into itself? So what you do is you look at projection from a point. So this is degree d minus 1. It's from projection from a point, and you take the same thing. You take the fiber product of that map with itself. And now, when you do that, if you take the fiber product of a map with itself, the fiber product, it contains the diagonal as an irreducible component. So you throw away the diagonal, and then when you get a z, this has degree d minus 2 in each direction. So. And it's realized by what do I want to say? The self product of projection from a point. Okay, and so how does this go? What's the idea here? So again, let me sort of show you how you prove this kind of a weaker inequality. So again, we're going to do the same thing as before. So it starts the same way. But so what's the kind of the Hodge theoretic statement? So the first remark is that for a very general X, if you look at the endomorphisms as Hodge structures of the primitive cohomology of X, that's just Z times the identity. And I'm not sure that, anyway, Radu Laza and Mark Green showed us proofs of this. I don't know whether it's in the literature, but in any event, so this is fine. So now let's argue as before. So let's consider as before a correspondence between X and itself, other than the identity. Okay, and let's pick a very general point Y. I'm sorry, Y is X, so this is X. So we're looking at a correspondence from X to itself. And let's pick a general point here, and let's look at its preimage. So let's say that B inverse of Y is delta point. So it consists of points X1 through X delta. So delta will be the degree of A. No, I guess it's the degree of B. Okay, now the point is that by step 1, by arguing as before, if we look at let's look at a differential form here, and let's do the same thing we did before there. So we take this differential form, we pull it up and we trace it down. So we take a form here, pull it up and trace it down. So again, this is a piece of this correspondence gives us a map from an endomorphism of the primitive cohomology of X. And by this previous step, this has to be a multiple of the identity. So this has to be C times eta for some constant C, right? Because this is the N0 piece of an endomorphism like this. And so what that means is that C times eta of Y has to equal the sum of eta of X1 plus eta of X delta. So now these, we don't know that this is a null trace correspondence, but we do know that for any point Y, the multiple of the eta Y is the sum of these, the values of eta at these points. And so just as before, this means that we can't have an N form, an N0 form. Well, we can't have an N0 form vanishing at all but one of these points and not at the other. So form vanishing at, let me say it differently, that let me not write it down, that any form that vanishes at these points must vanish at this point as well. So just as before, this gives us by separation, by this sort of Cayley-Backward thing, as before, this, as above, this implies that this delta plus one, these delta plus one points can't impose independent conditions on, so these, the X's together with the Y can't impose independent conditions on N0 forms, so there must be at least D minus N of them. And so this shows, this is the sort of weaker thing, this shows that delta is at least D minus N minus one, but then with some further work involving, spanning by lines and so on, this will give, hopefully, this will give this stronger statement. Okay, so that's this story about these correspondence degrees. And so now, so as I say, this is the analog of this correspondence degree is the analog of the invariant given by the measure of irrationality given by the degree of irrationality. So the other thing we talked about in the previous hour with measures of irrationality is invariance defined by the geometry of covering families of curves. So I want to now talk about how that goes in this context. So joint covering invariance. And here it's interesting. I mean, these seem to be much more subtle, and they're really almost, there's a definition here, but it's almost fair to say that there are very few results. But you have to, so the question is so we're given X and Y. So we're given X and Y. And we want to sort of look at families, we want to sort of look at invariance defined, measures of association between X and Y defined by covering families of curves. And so the idea is we're going to study families of curves that simultaneously cover X and Y. So study families of curves that simultaneously covering X and Y. Okay, so how should we define that? So here's the definition. So we'll define the joint covering gonality of X and Y. So we'll just use this covering gonality XY. This is called the joint covering gonality of X and Y. So we're just going to take the minimum over all correspondences Z as before of the covering gonality of Z. And similarly, the covering genus of X and Y will be the minimum over all correspondences Z of the covering genus of Z. So in other words, if we look at this picture, if we have Z here, we're kind of looking, we have X and Y here, we're looking for families of curves parameterized by some variety T so this is a family of curves C sub T, and we look at families of curves that cover Z. So if we have a family of curves covering Z, it gives us a family covering X, and it gives us a family covering Y. So it's a family of curves that simultaneously covers X and Y. And conversely, if you have a family of curves simultaneously covering X and Y, you can find a Z that you can find a correspondence that is covered by these curves. So we're looking at families of curves that simultaneously cover X and Z, and we want to know what can we say about their gonality and what can we say about their genus. Well, so there's one kind of silly inequality we can note, is that kind of definitionally, the joint covering gonality of X and Y is at least equal to the maximum of the covering gonalities of X and the covering gonality of Y. And to say that equality holds, and ditto for the genus, and to say that equality holds means that you can find a family of curves computing the covering gonality of X, say, that also covers Y. So in that sense, it measures the extent to which curves covering X are different or the same as curves covering Y. So an instructive example here is to look at the case of abelian and K3 surfaces. So this is kind of an instructive example. So let's take S1 and S2 to be K3 surfaces. Okay, now remember that a K3 surface always is covered, there's always a one-dimensional family of singular elliptic curves covering it. So the covering genus of a K3 surface is 1, and so its covering genus is 1, and so its covering gonality is 2. And but the claim here is that in fact this is also computing the joint invariant. So the covering genus, the joint covering genus of S1 and S2 is also 1, and so the joint covering gonality is 2. And why is that? Well, the point is that this should be SI. The point is that on a K3 surface, any K3 surface is covered by a non-isotrivial family of elliptic curves. So that means you can find essentially all elliptic, if you take the K3 surface number 1, there's essentially all elliptic curves lie on that. You can find a family of elliptic curves on that thing that dominates the moduli space of elliptic curves. And same thing of S2. And since these families dominate the moduli space of elliptic curves, you can kind of map to take a fiber product over moduli space, and you can kind of untwist the family. So any family, a non-isotrivial family that dominates S1, and a non-isotrivial family that dominates S2, since they contain essentially all elliptic curves, you can find a bigger family that dominates both S1 and S2 together. Okay, on the other hand, what happens if you look at abelian varieties? So let's say that abelian surfaces. So let's say that A1 and A2 are very general abelian surfaces. So, I mean, let me just do the gonality, but it's the same thing for genus. So then, remember, any abelian surface contains a curve of genus 2. So then the covering gonality of AI is 2. For example, if it's principally polarized, it is the Jacobian of a curve of genus 2. But the point is that what happens so let's say on a surface, abelian surface A1, you can find this curve of genus 2, and then it covers it, but it covers it because you can translate it. So each of these two abelian varieties contains a curve of genus 2, and they cover because you can translate, but the curve of genus 2 on A1 doesn't have anything to do with the curve on genus 2 on A2. So in fact, in this case, the joint covering gonality of A, you can show that the joint covering gonality is at least 3. And I think it's 4, but I'm not sure that that's completely known. So you see, somehow what's happening here is that these A1 and A2 they both contain, I mean, unlike the case of K3 surfaces, they're both covered by curves of genus 2 or gonality 2, but they're different. The curves on A1 have nothing to do with the curves on A2, so the joint invariants are bigger. Okay, and so this is and then as before, there are some upper bounds. There are some upper bounds on these joint invariants in terms of the single invariants. So you can show it's elementary that the joint covering gonality of X and Y is less than or equal to the product of the covering gonality of X and the covering gonality of Y. And there's a similar statement for the genus, although it's not the product. It's multiplicative, but there's some coefficients that come in. But in any event, similarly for the covering genus. So it's bounded above multiplicatively. Okay. Okay, so what can you say about this? Well, okay, so let's start with the case of curves. And incredibly enough, these invariants seem to be already rather subtle for the case of curves. So let's let X and Y be curves. So let's consider curves X and Y. Curves X and Y. So what is, for example, the joint covering genus of X and Y? So the joint covering genus of X and Y, so let's say they consider curves of genus GX and GY, and let's say that these are, I don't know, it doesn't really matter. Well, let's make, okay, of genus GX and GY. So what you're looking for, the joint covering genus of X and Y. So by definition, what this is you want to find the minimum genus of a curve that covers both X and Y. So this, by definition, is the least genus of a curve that covers least genus of a curve, a curve that covers both X and Y. So it's a very concrete thing. Covers X and Y. So given two curves, I'm asking just the very concrete question, what's the least genus of a curve that covers both of them? And amazingly enough, that I don't think the answer, it isn't at all clear what the answer is. So for genus, there's something you can say anyway, even if I don't think it's completely, it's not optimal, but at least it has the right shape. So let's see. So let's assume that X and Y are very general. Assume that X and Y are very general curves, and maybe genus at least 2 or something of genera. Let's say of genera GX, GY at least 2. Then what's at least true is that the joint covering genus is multiplicative. So the joint covering genus you can find if you have 2 very general curves of those genera, it's less than 5/4 GX times GY plus some linear term in GX and GY. And it's at least equal to the product of GX times GY plus some linear term in GX and GY. So in any event, if you take 2 very general curves, in any event, the covering genus grows, is at least multiplicative in the genus. And again, the lower bound you get by just taking the gonal maps. You express X and Y as branch coverings of P1 of minimal degree, and then you take a fiber product. And this lower bound is you can get something just out of Riemann-Hurwitz. This is a little bit this is a little bit trickier, but it's an infinitesimal computation. But at least you get a multiplicative statement. But what's strange is that I have absolutely Olivier and I are unable to prove anything at all seriously about the covering gonality. So we don't have any non-trivial bounds. But the conjecture is that for very general X and Y, the guess would be that the covering gonality should grow multiplicatively. So the covering gonality of the joint covering gonality of X and Y grows multiplicatively, grows multiplicatively like gx times gy. So if I take a very general curve of genus gx and a very general curve of genus gy, the conjecture is that the smallest canality of a curve that covers both is multiplicative in the genus. But this is, we don't see how to say anything non-trivial. Now, there has been some progress by Nathan Chen, Gabi Farkas, and Riji Yang, and they show, and it's not 100% clear what the current status is, but let me just say they've made progress under some additional hypotheses on the curves. But as far as I know, the sort of the general, and if you take two general curves, unless these guys or somebody else has made some substantial progress recently, I think it's completely open. And in fact, it's only with some effort that Olivier and I can treat the case of hyperelliptic curves. So let's suppose that X and Y are very general hyperelliptic curves of genus at least 3, hyperelliptic curves of genus at least 3, then the covering ganality is 4. The joint covering ganality is 4. So the covering ganality is less than or equal to 4 just by this the dumb inequality on the upper bound, that the joint covering ganalities is at most the product of the ganalities, but it's equal here. And this uses some of these specialization arguments in the spirit of Pirola, Voisin, Martin. Okay, so even for curves, it's non-trivial. What about hypersurfaces? So again, they're very weak results that are known, but conjecturally, the picture should be much stronger. So I'll tell you what the proposition is. So let me recall that, well, let me just tell you what the proposition is. So the proposition is that if we take XD and YE, very general hypersurfaces of large degrees, general of degrees greater or equal to 2n plus 2, let's say. So degrees D and E greater or equal to 2n plus 2. Remember that the covering ganality of D and the covering ganality of X is essentially D. Asymptotically, it's D, and the covering genus is asymptotically D squared over 2. And so the statement is that you get added for these joint invariants, you get additive bounds. So the covering ganality of XD and YE is at least D plus E minus something or other, 3n plus 2. And the joint covering genus is XD and YE is at least D squared plus E squared over 2 plus lower order terms. So this here is the sum of the D and E are asymptotically the individual covering ganalities, and D squared over 2 and E squared over 2 are individually asymptotically the covering genus, but so it's an additive statement. But the conjecture, I'll just state it for covering ganality, is that it should grow multiplicatively. So the conjecture is that the covering ganality of XD and XE should grow like D times E. And similarly, the conjecture is that the covering genus should be a little bit bigger. So you can, okay, so that's, so again, I think there are these covering invariants sort of leave a lot, they kind of seem to be much more subtle than these degree invariants. Let me end with some 2 questions, and then so here are some. So one thing that would be very nice is remember that in the case of the degree of irrationality, Chen and Stapleton were able to use these characteristic P arguments of specialization of characteristic P of Collard to get bounds for the degree of irrationality in the Fano range. So the question is, can one find bounds for the correspondence degree of two very general hypersurfaces in the Fano range, so where D and E are small, in the spirit, you know, a la Chen, let me say Kolar, Chen, and Stapleton. So Kolar, Chen, and Stapleton. So can you use some of these ideas to get even weak bounds for the correspondences in low degree? And then going back to abelian varieties, you could ask for, can you say anything about these invariants for these covering invariants for abelian varieties? So let's say A1 and A2, very general abelian varieties, varieties of dimension n. And then can one say anything about sort of lower bounds? Can you give any kind of lower bounds on the joint covering gonality of A1 and A2? So this was the first single abelian variety. This is what Voisin and Olivier did, or the covering genus. So there's been a fair amount of work on what's the minima genus of a curve on a given abelian variety. But can you say anything about these joint covering invariants? So in the spirit of Hurola and Voisin and Martin. And then finally, I won't write it down, but another question, I don't know if there's anything to say, but we've said that this correspondence degree, when you take the logarithm, it gives a metric space structure to the set of all birational equivalence classes of varieties of fixed dimensions. So, you know, people have looked at various invariants of metric spaces. So is there anything you can say about the structure of this metric space? So I don't know if there's what the question would be there, but anyway, it's one could, you know, there's a metric space there. Is there anything to be said about it? Okay, so anyway, that's the story here, and I thank you for your attention, and I'll end there.